Let's talk about z-scores. So I actually want you to first start by pausing here just to sort of remind yourself of how to do this. So the mean weight of a sample of 1-year-old girls is normally distributed if 68% weigh between 20.3 and 26.7 pounds. Find the mean and the standard deviation of this distribution and represent the information on a normal curve. So pause here and do that, please. Okay, so the way that I did this, again, there is not one way to do this. There are a few ways to do this. Here, I knew the 68%, that should ring a bell in my head. That has to do with our normal distribution with the probabilities, right? This is the empirical rule. We know that for any data that is normally distributed, 68% will fall within a standard deviation of the mean. That means one standard deviation over and one standard deviation under. So here is 20.3 and here is 26.7. My mean is right in between them. So I find the difference, it's 6.4, and I divide by 2. The reason that I'm dividing by 2 is that there is one standard deviation, two standard deviations between these two observations, right? The mean is in the middle. 6.4 divided by 2 is 3.2, so the standard deviation is 3.2. And then to find the mean, I just go up one standard deviation from this 20.3, and I find a mean of 23.5 pounds. So this is what your probability looks like for the normal curve. This should be pretty well in your head. You see, we have the 68% within one standard deviation, about 95% within two standard deviations, about 99.7% within three standard deviations, right? Almost all observations in normally distributed data will fall within three standard deviations of the mean. But please notice, these are on precise standard deviations, right? So 34.13% of observations will be within one standard deviation. I don't know what the percent is for observations that are like 1.2 standard deviations out. So that's what we're going to do today. So the z-score is the area under the curve associated with standard deviations from the mean, just like the empirical rule, except for these are not only exactly at whole numbers. Obviously, these are positive 1, positive 2, positive 3. We need the z-score to get numbers between whole numbers. And of course, because most observations will be within three standard deviations, that's going to be true for the z-scores as well. The real reason that we need the z-score is that a standardized score allows us to compare across different distributions. I'll show you what I mean in a moment. So first, let me just show you what this does. So you can have any normally distributed data. This could be SAT scores, it could be heights, it could be weights. We're going to have whatever our mean is, we call it mu, and whatever our standard deviation is, this is sigma. This process of finding the z-score basically turns this distribution into a distribution where the mean is 0 and the standard deviation is 1. Again, what this allows us to do is it allows us to compare across different distributions. So there are two z-score formulas, one having to do with a sample and one having to do with a population. They're the exact same thing. The symbols are different because the symbols for population and samples are different, but it's basically the exact same thing. The z-score is the observation or the individual score minus the mean over the standard deviation. Same thing here, except for we're using the symbols for standard deviation and mean at the population level. We're going to talk more about sample and population later in the course, but for now, it's not super important. You can use either one of these depending on what you have, what information you have. Okay, so let's do an example. So let's say that Juan took both the LSAT and the MCAT. He scored a 172 on the LSAT and a 37 on the MCAT. Assuming scores for both are normally distributed, and using the summary statistics below, find out which exam he did better on. So you might think, well, he got a 172 on the LSAT. That's definitely better than the 37 on the MCAT. But these are on different scales, right? We do not have enough information with the raw scale. That's why we need to standardize, right? We need to put these on the same exact scale so we can say, which one did he do better on? And the way that we do that is by finding out how many standard deviations away from the mean he is for both of these. So we're going to standardize it. We can see right away that he got a score above the mean on the LSAT. So his score, it was 172, and the mean LSAT score is 151. And what about the MCAT? Let's see, he got a 37, and the mean MCAT score is 25.1. Great. So we don't have enough information yet to say which one he did better on, because he did better relative to the mean on both of them. How much better than the mean did he do? That's basically what we're asking. So I'm going to use my z-score formula for both of these. The observation minus the mean, the observation in this case is what he got on the LSAT, divided by the standard deviation for that test, and I get 2.1 for the LSAT. For the MCAT, it's the exact same formula. The observation is 37, that's what he got, minus the mean of 25.1 over the standard deviation for that test, and he got 1.86. So on the LSAT, he scored 2.1 standard deviations above the mean. And on the MCAT, he scored 1.86 standard deviations above the mean. So in this case, he did better on the LSAT than he did on the MCAT. On both tests, he did better than the mean person who took the test. But in this case, he did better on the LSAT because he was 2.1 standard deviations above the mean. Here, he was 1.86 standard deviations above the mean. All right, so now it's your turn. A miniature dachshund and Labrador retriever are playing together. The dachshund is running at 10.8 miles per hour and the Labrador is running at 19 miles per hour. Using the summary stats below, figure out which dog is running faster relative to its breed. So pause here and go through those steps, please. All right, so we have the same z-score formula. We do the observation minus the mean. Observation minus the mean. Please note that both of these dogs are running below the mean. So 10.8 is less than 13 and 19 is less than 22. So both of our z-scores are going to be negative, right? Because our mean is going to be greater than our observation. So we divide by the appropriate standard deviations for each breed, and we see that the dachshund was running 1.38 standard deviations below the mean for dachshunds, and the Labrador was running 1.07 standard deviations below the mean for that breed. So the question is, figure out which dog is running faster relative to its breed. Okay, so faster relative to its breed. So faster is above the mean, right? But one is still going faster than the other one. So this dachshund is about 1.38 standard deviations below the mean. This Labrador is really, 1.38 is going to be about here, and 1.07 is going to be like just here. So actually the Labrador is closer to the mean, right? So sometimes when you read these problems, you have to ask, what is it talking about? What the z-score is going to tell you is how far is this observation for the mean. These two different dog breeds have different standard deviations and different means. So that's why we standardize, so that we can talk about them in relation to each other. Okay, so that's what z-scores do. A major sort of what we're going to be doing for the next little while is you're going to be finding probabilities using the z-score. We've already started this by using the empirical rule. Remember, that's the 68, 95, 99.7. This actually translates pretty easily into the z-score. The only tricky thing is you're going to have to get to know this table, B1, pretty well. So you can see just from this normal curve, you already know these probabilities, right? This is the empirical rule. You already know these. So instead of having standard deviation here, I just put Z. That's really what the z-score does, right? It standardizes so that you have a mean of 0 and a standard deviation of 1. So you already know these z-scores. This table B1 is going to let you know the area or the probability for non-whole numbers. Okay, so table B1 is on Canvas. It's also in the back of your book. It's on page 373 of your book. So you should find it if you have your book on you, just because it's maybe a little bit easier to read on the book, or you can use the one on Canvas, either way. So the way that you read this table, it's sort of weird. It's actually only a 2-column table, but they're looped, right? Because otherwise you would just have this really sort of skinny table on many, many, many pages. So the 2 columns that go together are the z-score and the area between the mean and the z-score. But it's sort of formatted in this weird way where it goes all the way down and then down the next page before looping back. So pause here, find the table, and I want you to find z equals 331 and z equals 332. Okay, so here at the bottom of this page is z equals 331, and then you go to the next page to find 332, and then this is going to go down, 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 down before coming back up to the top of this page. It's only a couple pages, but it is kind of hard to read when you have it in the book. It's actually maybe not as hard online. Maybe you should use this one that I'm showing you. But this is the z-score. This is the area under the curve. This is the z-score. This is the area under the curve. So the way that you read it is the column that says area between the mean and the z-score. That actually gives us the probability that an observation is between the z-score and the mean. So again, I said earlier that we're just going to be sort of skipping over some of the math. This has to do with area under the curve. We're just going to call it probability. And we are going to not talk about why, but if you want to know why, I'm happy to talk to you about that. So now I want you to look at table B1 and I want you to find z equals 1.00. What is the area? And think about where have you seen this information before. So pause here, look at your table and find z is equal to 1. So here's a snip of the table. You can see here the z-score is 1 and the area between the mean and the z-score is 34.13. Where have you seen that 34.13 before? Oh, this is the empirical rule, right? We know that 68% of all observations are between -1 standard deviations and +1 standard deviations. So that's basically half of that 68%. You should have, this number should sort of be getting in your head by now. All right, so I want you to pause here and I want you to find z is equal to -2 and the associated area under the curve. So hopefully you looked and you saw, there actually are no negative numbers on the z table. That's because the normal curve is perfectly symmetrical. So whatever the area under the curve is at z equals 1, it's the same area at z equals -1. Same thing with 2 and -2. All of the positive numbers are reflected in the negative numbers. So if we wanted to find z equals -2, we would just find z equals +2. And here you see, okay, the z-score is 2. And the area between the mean and the z-score is 47.72. That number should also actually be familiar. So if you look back at our normal curve, 47.72, this is, the original question was about -2. But again, there's symmetry, but I'll show you -2. It'll be the same thing for 2. So at -2 standard deviations, which is the same thing as z is equal to -2, we have this area under the curve, which we're going to be calling probability, and we have this area under the curve. We add them up and we get 13.59 plus 34.13 equals 47.72. So that's the relationship between the z-score and the area between the mean and the z-score. you should always, always, always be drawing a normal curve and marking it out. It makes it way easier. Okay, so those were whole numbers, but the great thing about table B1 is that we can find area under the curve for any number. So if we wanted to place z equals 0.50 in its approximate location on a normal curve and sketch the corresponding area under the curve, that's going to look like this. So this is 0 standard deviations away from the mean, right? Because this is the mean. This is 1. So here at this red line, this is about 0.5. This is a z-score of 0.5, and that's what we're looking for. And then the area, remember this is the area between the mean and the z-score, so this yellow is the area underneath. And I have here that the area equals 19.5. How did I get that? Well, if you look at your table B1, you just find the z-score of 0.50, and the area between the mean and the z-score is 19.15. So the way that we're going to read this 19.15 is that, let's say that we have all adult women in the U.S. The probability that we are going to randomly select somebody that is between the mean and 0.5 standard deviations from the mean is basically 19.15%. All right, so I would like you to pause here, and I want you to find the area between z is equal to negative 2.25 and z equals 1.50. Please, please, please sketch. It really does help. Okay, so first I have 1.50. 1.50, okay, I'm 1 standard deviation from the mean. Here's 2 standard deviations, so halfway between 1 and 2. Boom, that goes here. And I sketch in the area between the mean and this z-score. Well, how do I know what this area is? I go to my table B1, and the z-score for 1.50 has an associated area between the mean and the z-score of 43.32, okay? So boom, this blue, all this blue, this is 43.32. And then here is negative 2.25. Just because your table B1 doesn't show negative numbers doesn't mean that you can't be negative z-scores away from the mean. You absolutely can be. So here's negative 1, here's negative 2, here's about negative 2.25. So I put my red line here, and then I sketch in this area. And remember, the area is between the mean and the z-score. So in this case, if I want to find the area between negative 2.25 and positive 1.5, I would add these up, right? And you can see that when you sketch it, that of course you need to add it because you want all of this over here and you want all of this over here. So basically what this means is that there's a very good shot if you randomly select somebody from normally distributed data, there's a 92.1% chance that they're going to be between negative 2.25 standard deviations from the mean and 1.5 standard deviations. That should be pretty intuitively obvious to you, because you know that from the empirical rule that about 95% of observations will be between negative 2 and positive 2 standard deviations from the mean. So in this case, you can see that we have a z-score on the left-hand side of the mean and a z-score on the right-hand side of the mean. I'd like you to pause and do another example. Both of these z-scores are on the left-hand side of the mean. I want you to pause, I want you to draw your normal curve, and I want you to sketch in the area under the curve. Okay, so we have 2 observations on the left-hand side of the mean. So first, let's start with our negative 2.25. We already did this one. We know that 2.25 has an associated area of 48.78. So remember, this is between the mean and the z-score. So the green is all of this, between the mean and 2.25. The other z-score is also on the left-hand side of the mean, and this is at negative 0.5. Here's negative 1 standard deviation, so this is half of a standard deviation. So this yellow part, we already saw this too, actually, that a z-score of 0.50 has an area of 19.15. For the previous example, both z-scores were on opposite sides of the mean, so we added them. What do we do in this case? Well, we actually subtract them because we take our whole green piece, but that's not the question. The question is not what is the area between negative 2.25 and the mean. The question is what is the area between negative 2.25 and negative 0.5. So we take all this green and we subtract this yellow piece, right? This is the area for the yellow piece. And what do we get? We get an area of 29.61. So what that means is that a randomly selected observation has a 29.61% chance of being between negative 0.5 standard deviations from the mean and negative 2.25 standard deviations from the mean. Okay, final example. A lot of these questions that you're going to have to do for lecture check and for group work and for quizzes coming up is something like this, where you're going to have to do a few steps. So, if the length of newborn alligators is normally distributed with a mean of 6 inches and a standard deviation of 1.5 inches, what is the probability that a newly hatched alligator will be between 5 inches and 7.5 inches? So first I want you to find the z-scores, then I want you to draw the area under the curve using these two z-scores in their approximate locations, and then I want you to convert the area under the curve to probability. So pause here, please, and take a few moments to do that. Okay, first things first, I find the z-score. So 5 inches, this is our observation, minus our mean divided by our standard deviation, we get a z-score of negative 0.67. And then 7.5, here's our observation, minus our mean divided by same standard deviation, right, because we're talking about the same distribution, and that's at 1. Draw the area under the curve using these two z-scores. So we know that 1, boom, has this area of 34.13. That should be in your head by now. And negative 0.67 is about here, right? This is halfway. This is maybe 3/4. So again, it doesn't have to be all the way accurate. This is about where negative 0.67 should be. And this area is 24.86. How did I get that? I looked at table B1, and then you can see these z-scores are on opposite sides. So what do we do? In this case, we add them. We're not subtracting in this case, we're adding them. So we add these together, we get 58.99. And the final step is to talk about this in terms of probability. So when I say convert to probability for area under the curve, it is the exact same number. You're really not doing much. You're just trying to think about what this means. So the probability is 58.99, so just about 59%, that a newly hatched alligator will be between 5 inches and 7.5 inches.